So we have previously shown that we basically have a sequential or combinational logic. So if you have like any clocking methodology, so this basically means that we will need a sequential logic. So you can have like a certain particular state, let's say like state 1, which will go to state 2 at the positive, each positive edge of clock, you are changing the state. However, in between, you can have like a combinational logic that will do basically a certain particular task. And we will see that, of course, when we begin to implement the mini CPU over the Verilog. You will do something like that, exactly, the same exact concept. So we need to understand how we can build a data path. The data path means from the very beginning when we fetch the instruction, meaning I am fetching the zeros and ones, until I execute whatever like these zeros and ones means. This is basically the data path from the very beginning till the very end. We need to see how we can build the blocks in order to satisfy that particular requirement. This is what we will learn. We have, as we have covered earlier, that we have instructions like add, multiply, subtract, load word, store word, branch, jump, and all of these kind of things. And of course, each of these might need a little bit different implementation blocks. A little bit. It might need, it might not. This is what we will understand in this particular chapter. So we will build a MIPS data path incrementally, and then refining, of course, with the overview of the design. So at the very beginning, I need to do an instruction fetch as we have described earlier. Fetching means what? I have to read the instruction from the instruction memory. I have to update the program counter value to the new address. So if this is my memory or instruction memory, I have an instruction after the other, and so on and so forth. First of all, I need to take the corresponding instruction that has to be fetched appear here at the output, correct? So I have to push that instruction from the memory that it will appear at the output. This is the instruction that I would like to decode and then execute. This would be the first step. As soon as I'm doing that, in that particular step, I have to update my program counter, which was pointing to that particular instruction, to be added to 4, and then I will have a new value that basically will point out to the next instruction to be executed. And this happens at the same time. So each time my program counter will be advancing to the next instruction to be executed. Normally, it will be program counter by +4, but this is not always. Because if I have a branch instruction, as an example, I don't have only to add 4. I have to add 4 plus the branch, as we have covered earlier. Also, as I told you, that we can play with this number. If the instruction itself is 32, but for some reason the width of this memory, instead of 8, I have the width here is 32. If I have the width of this instruction 32, so of course I don't have to each time increment by 4. Instead, I have to increment by 1 in order to go to the next instruction to be executed. So I'll just go one after the other, and so on and so forth. So just like for the normal case, I have each time I'm pushing an instruction to my output, that my program counter will be updated to the next instruction to be executed. And my job is knowing exactly what will be the instruction or the next instruction to be executed, or how to calculate the address of the next instruction to be executed, or how I will tell the address to my robot to go and fetch the next instruction. So PC is updated every clock cycle, so it basically doesn't need any explicit write control signal, because this is something happened automatically each cycle. But reading from the instruction memory is basically a combinational activity which does not need any explicit read control signal either. So with this instruction memory, I don't need to have like a read or write signal, because this has happened just if every cycle. I have to fetch, I have to update the program counter. I have to fetch, I have to update the program counter. So I don't have to have an external signal say like, hey, read. Because each clock I'm doing the same exact thing. Yes? As we will see later, that this is not always the case with other blocks. I might have the clock that actually will do something, but in other cases, I don't have to write or I don't have to read. That's why I have to have an extra signal that will control the write and the read. So meaning that the write and the read will not happen with every cycle. So basic architecture with the control unit. So we just like see if we have an instruction memory. So instruction after the instruction, what's exactly happening with the program counter as with the register, and we'll see like with each of these how we will do the fetch, decode, and execute. It's just like from the basic point of view. If you look closely at this one, at the first instruction, yeah, this is called the first instruction, correct? I cannot call it the 0 instruction, just the first instruction. But the first instruction will be address 0. So the first instruction, RF of 0 is equal to D of 0, as RF is basically the register, D is referred to the data memory. So now I am copying something from the data memory at location 0 to a register file at location 0. What is that corresponding, or what is that instruction corresponding to the MIPS? So I'm moving something, or I'm copying something from the data memory to the register file. So this is basically not but load word. Load word, I'm going to copy something from the data memory to the register file. With this, it shows you that it will take that from address 0 and it will copy to address 0. So meaning that I'm copying the first basically slot in the data memory to the first slot in my register file. So at the very beginning, my program counter, as you can see here, is basically 0. And then I will begin to fetch. So I will take this to my instruction register, and then I will decode. After I decode that, I will understand that this is basically load. Yes, because I don't know in advance if this is load or not. I have to fetch it and then decode that instruction. After that, I will know that this is basically a load instruction. Then I have to execute that. Of course, if I found that in the D of 0, the value that is 99, what I'm expecting the value here at the R of 0 is basically to be exactly the same. So this means I'm copying the 99 to the register file, so I have the 99. So next, I will go to do the same things for RF of 1 equal D of 1. So this is exactly the same as before. The only difference that I'm, instead of copying the location zeros, I'm copying the location 1. So we'll see like it's showing exactly the same things. I will fetch and then I will decode. I understand that this is again load. As you can see, my program counter has been updated to the next instruction to be executed, assuming that I'm just counting by 1 in this case. And if my data is 102, of course, my register will also be 102. Look at the third instruction. I would like to add a certain particular location in my register file to another particular location, my register file, and allocate the results in actually a third location file. So I'm adding the location 0 plus location 1, put results in location 2. This is not but add. It's an add instruction. And as you can see from here, with the add instruction, we did not touch the memory at all. With the load, we have, of course, to touch the memory. If we have a store, we have also touched the memory. But with R type, we don't have to touch the memory at all. So we'll do the same exactly. I'm incrementing the program counter, and then I will decode. I will understand that this is an ALU add. And then after that, I have to execute. So basically, I have to add whatever I had in the previous one to the one before, which is 102 plus 99. So I have now the results in the 2 location as the addition, which is 201. Next, I need to do this guy. What is that guy? D of 9 is equal to register file of 2, meaning that I have to store what? I have to store whatever I had already calculated, which was the 201 that I had already saved in the RF of 2, to the 9th location in my data memory. I need to do exactly the same things as we have described. The only thing that now it will understand that my decoding is basically a store word, and then what it will do is at the end it will copy this to the data memory. It just showed you like step by step how things is happening, but I'm not expecting that I have already explained something new. All of you are basically aware of all whatever I have described right now. So going back to the data path that we have already explained earlier, that with each of the fetch, I have to update the program counter to the program counter +4, and then I have to decode, and then I have to execute. So this means that I will take my instruction. This is from the instruction memory. I have to take that guy and then decode it. Why? Because from the decoding, I will know which type, R type, I type, J type, and if it is any of the type, I need to know what exactly I have to do. So for instance, if this is where to be like an R type, an R type meaning that I am expecting that this guy will show me the first source, this guy will show me the second source, and as soon as I am pointing to a certain address here, that particular location will appear at the output. As soon as I am pointing to a certain address here, that location will appear at the output. In another sense, I'm telling you, please, with this guy, go to slot number 5 or mailbox number 5. As soon as I'm telling you, please go to mailbox number 5, you have to go and open the mailbox and take everything that is inside that mailbox, correct? Taking everything that is inside that mailbox, meaning that I have to have the data that is inside that particular slot outside my register. Exactly the same things with this guy. As soon as I'm giving you the address of the next slot, my next mailbox, let's say the 9th one. As soon as I'm pointing out to the 9th one, you have to go and open the mailbox and take out everything that was inside, which will appear here at the output. Correct? Without knowing even that if I'm doing an addition or subtraction or whatever it is, I just knew that this is an R type. I have to do this. We will see later on with a lot of the other types what exactly I have to do. But just like before that, let's say that we would like to write that particular step in Verilog. How we can do that? So I will have my program counter, and then each time the program counter will be updated to program counter +4. How to write like a simple Verilog code for something like that? I have to define, of course, all my inputs and outputs. This guy will be each time like updating the program counter. I have to have, of course, an input called clock and an input called reset. And this is always with any sequential machine, correct? I have to have a clock and I have to have a reset. If I would like to reset all of my data, I have to have a bottom that basically when I hit reset, everything will be 0. And the output of this program counter. The output of this program counter is how many bits? It's basically 32 bits. And that's why I'm defining my output as a 32 bits. And I have defined it as a register here because I have an always block and the PC actually in the left-hand side inside my always block, as I have described earlier in the slide. That's why I have to define this as a register. Or, just like for your information, since this is an output, in some other cases, I don't have to define it as a register since it is an output. Yes? So in some other cases, since it is an output, I don't have to define it as a register. I have also to define these 4. So I will define like a parameter which called like increment amount. And this basically is decimal 4 and it will be written in 32 bits. So this means that this guy is basically the increment amount, which I'm defining at this one. And I'm saying that with each clock or with each positive edge clock, please, if I have an update signal, update the program counter to the program counter +4 in this particular case. By the way, I can change this guy to any other value if it is required. So if reset, meaning if reset is equal to 1, reset the program counter, meaning the program counter need to be 0. Otherwise, if the reset is 0 and I have the update signal, please increment. This is just a simple Verilog code to show you like how to write something like that. I can also have the same exactly things, but instead of having 4, I cannot make it like as an input, which have like a certain instruction side. Yes, so this actually basically will be always as an input. So I will not like define it in advance as 4. It can be a certain input, whatever like I will have with my mechanism. Because as I told you earlier, it doesn't have to be always 4. Correct? And as you can see from the rest of the code, it's exactly the same. If reset, this is equal to 0. Else, if an update, please update my program counter to program counter plus the instruction size. So looking back to the R format instruction, we have the opcode RS, RT, RD, destination, shift amount, and then function. So at the very beginning, I will go to the opcode and will decode that. I will understand that this is an R type. As soon as I know that this is an R type, I have to do a certain particular tasks. First, I have to read the RS and know exactly which of these slots will appear at the output. I have to read the RT and know which exactly of the slots need to appear at the output. And I have to know the RD in order like to know where exactly I have to write my data back after I finish my operation or after I finish my execution steps. So this will be the first thing to do. After I have this guy, now this ALU will do a certain particular instruction. Either I will do addition, multiplication, division, whatever it is, and the command will come from here, the ALU operation. Meaning there is a signal input to the ALU that will basically inform the ALU what exactly to do. How I will get these results? ALU operation, of course, after I decode the function, I will know, for instance, that I have to do addition, or I have to do subtraction, or I have to do whatever I need to do with this particular R-type instruction. And it will just like inform the ALU what exactly the ALU need to do. Let's say I have the output here results, and let's say that I have already done the addition. Okay, so now I have the addition results. What I need to do afterward? Basically, I need to dump that particular data to a certain particular location, which defined by the destination register. From the destination register of this address 5 bits, I already knew that as an example, I have to dump it in this particular location. But I have to have physically an input that I will connect this output to in order to dump the data. And that's why I have here an input called data or write data. This is basically will be my pipe that will hold all of these bits and dump it in that particular mailbox slot. Because I have to have physically something that will take that data to that particular slot. So what will be the case if I having a load or a store operation? Just to remind you, store, it will read from the register file during the decode and then write the stuff to the memory. The load will be the other way, read from the data memory and then write to the register. But physically, how we can do that? Just to remind you of the load word as an example. The load word will define a couple of things. First, it will define from where I should grab my data, correct? From where? From where it will be defined by two things. What is my base address and what is the offset, correct? So I know in advance right now that I need my ALU to do either an addition or subtraction to calculate what is exactly the address, because with that offset, I might add or I might subtract. Correct? So I know now in advance that I have to have the ALU in order to execute my load word. And the same apply for the store word, correct? Because I have to have a base address plus or minus a certain particular offset. So I will need that guy. I will need this ALU. But this ALU has two inputs. This ALU basically needs two inputs. One input will be the base address, and the other input will be the offset. correct? However, if you remember back to our I type, the offset is how many bits? The offset, if you remember with the I type, that is opcode, and then RS, and then RT, and then this offset is basically 16 bits. But when I do the addition here, this guy with another guy that is coming from here, this guy actually is 32 bits, correct? Yes, by your eyes, you can actually add 32 bits to 16 bits, but now we need to make everything in automation. We have to have our robot to add a 32 bits to another 16 bits. How I can do that? How the robot will understand how many or what exactly the values of the 16 bits that is basically rest. So I have a 32 bits that need to be added with the 16 bits, correct? How the robot will understand how exactly these values, the rest of the 16 bits. So I have to make sure that I will do what we call the sign extension. That basically I will allocate these 16 bits in another 32 bits, correct? In order like when it will be added or subtracted, it will be added or subtracted to another 32 bits. So first of all, I know now that in order to do this addition or subtraction, that guy need to come from a 16 bits, sign extend to 32 bits, and then I can do the addition or subtraction. Correct? Because if you remember that offset, that particular offset will not be basically in any of the register file. Yeah. So let's say like load word, for instance, equal S0 and then 8 S3. Basically, I would like to go to S3, correct? And then add 8. So I will go to a certain particular here, which is basically S3 plus 8. And then I will take that, copy it to here. Copy it to where? To S0. So basically, I'm expecting that this S3 or the value of this S3 will come from here, correct? Because it is something that already has been saved inside my register. It is in location called S3. But where is this 8? It is not in the register file. Yes, it's coming from my instruction. So as soon as I am decoding the instruction, I will be able to extract that 8 and just like feed to that sign extension. It will be extended to 32 bits. Now I can easily add or subtract this guy, and then I will know that I am basically pointing out to that particular location. Afterwards, I will take that particular location. Please dump it to my register at a certain right address, which will be basically slot S0 in this case. Correct? The same things will be the store word, but I don't have to write it back. I will take it just from the register directly to the memory and save it there. So this is just like show this stuff in particular another color, as you can see here. One more thing I would like to highlight with the store word, I have to have this guy. Correct? Because actually with the store word, I have to have a physical pipe that will take the data that a particular slot in my register and copy it to the memory according to the address that is pointing out with this particular value, correct? I'm telling you, please dump this data into an address 100. So I will go to 100 and then please dump the data here when I have a store word, for instance. Correct? But I will not need that if I have a load word. Yes, that's why if I am combining the R type with the store word, with the load word, and so on, as we will see later on, it will be not as simple as that. You have like to add a lot of multiplexers here and there in order like to choose which one I have to copy, which one I have to add, which one I have to move, and so on and so forth. But we are just right now thinking about the blocks that is needed, or the main blocks that is needed, and we are building one after the other. And this is, by the way, how you need to think also when you design anything. Yes, to break down the problem to just a small stuff and then begin to build until you can satisfy that particular, you build a design that will basically satisfy all of the requirements of either your project or your company. And then if I have a load word, of course, I have to write this back to that particular place. So this is just like to summarize with the data path that we have covered so far. We have this guy. I have here a multiplexer because I might get the data directly from here, which will be the second source in case of R-type as an example, or I can have to add the 32 bits after extension, which I needed with the load word and the store word. That's why I have to have a multiplexer here. And this will be controlled by a signal called ALU source. I have to have another signal called ALU operation, which will be 4 bits. It will basically direct or inform the ALU what exactly you need to do, or what exactly the operation that you need to do. I have also to have memory write, memory read, because as you have seen, like I might go to the memory, but I don't need to read at that particular clock cycle because actually the data did not arrive there yet. Yeah, or I have to read. I don't need to read always with every clock cycle because the data that I really need to read has not been arrived yet to my register, for instance. With this guy, I have to have also another multiplexer. Why? Because basically in some cases I need to read directly from the memory. In other cases, in the R-type, I need to read directly what is the results of my ALU. So I don't have to pass through the memory at all. And this again will be controlled from the memory to register signal. I have also a signal here, register write, and so on and so forth. All of these, by the way, the blue signals are coming again from the control unit. If this will be the brain. So as I mentioned earlier, you will have blocks. But how you will operate that particular blocks, will be the job of that control unit, which will say like, hey, you can take the data from here. Please add this. No, take the value or take the data from that particular path, not the other path, and so on and so forth. Correct? So we have also a branch in instructions. And as you can see from here, that the branch in instruction, even though it is an I-type, it will not be implemented exactly at the load word and the store word as we have seen earlier in the previous block diagram. What we will explain now how I can implement a branch instruction. So although all of these instruction, meaning branch, load word, store word, are I-type, but they will be implemented a little bit different, especially with the branch. So I have, of course, to read the register operand. I have to do the comparison. So as soon as I have a branch, is equal or not equal, I have to do subtraction. Yes, as soon as I see like the branch equal or not equal, so I have to do a subtraction instead of the addition. So I will use the ALU and then subtract and then check for the 0 output. And as we mentioned earlier, if I have the subtraction equal to 0, that 0 output will be equal to 1, meaning that the subtraction is equal to 0. It is true. So if it is true, meaning that it will be equal to 1. Or the design that we had implemented here, this is basically what it means. In your design, you might change it. But just like I would like you to be aware with whatever we have right now, that if the branch equal is basically 0, so this means that I have a 1 or I have a true signal there. Also, I have to calculate the target address. Correct? Because with the branch, I need the most important things is to know what is the next instruction to be executed. So I have to calculate the target address, where I have to go next. Yes, so you have a list with all of the tasks that you need to do. This and this and this and this. And after you finish each task, you have to understand or you have to know what will be the next one. If you are just like assuming that that robot is just a post office, with the post office, man, just like going house or building after the building, yes? So he or she basically does not need to check every time that what is next. But assuming that finish the street, of course, that guy need to open like a certain list and know where exactly to go, correct? This is exactly with the branch. With the branch, it's not always the next instruction to be executed is basically the following one. Sometimes it's like that far. So that's why I have to calculate with each time like what will be the next instruction to be executed if I have a branch instruction. So I have, of course, to sign extent, but I have also to shift left 2 places because I need the word displacement. If you remember, with one of the lecture slides, when I have like something like that, and with the branch instruction, if you remember when I write 2, yes, and with that time we mentioned that it should be 2 multiplied by 4, yes, and then I need to do the sign extension, correct? Because that particular number will be in 16 bits. But I have to allocate that into 32 bits. But as you can see from here, I have to multiply it by 4 in order to get the word count, yes? Multiplied by 4 means I'm shifting left by 2, and that's why here I have to shift left by 2, and then after doing all of these things, I have to add these guys to the program counter plus 4. Let's try to see like how this is basically implemented. So we are, as you can see from here, I was just like taking this from before, which is basically updating the program counter plus 4. This updation of the program counter plus 4 will not update this value because now I have a branch instruction. So this guy needs to be fed to another particular step to calculate what is the address of the next instruction to be executed. First of all, I have to allocate this instead of 16 to be like in 32 bits, correct? After I have that, I need to multiply it by 4. Multiply it by 4, meaning I need to shift left by 2. After I have the shift left by 2, I need to add this to the program counter plus 4. And now I have my branch target, which will update that value. Also, I have to, with this particular branch instruction, to take my 2 inputs and subtract and check if I have a 0 or not. Correct? I have to have my 2 inputs because this will be basically the 2 inputs that I need to check if they are equal or not. And then subtract. And after I subtract, I will know from here that is right or wrong. Meaning it satisfies that branch or not. Because basically, if it is satisfying that branch, I have to go to that target address. If not, I have to go to that target address. Correct? Again, I'm always, as an example with that branch instruction, let's say like branch equal S0, S1, and then label. Correct? I will check if this is equal to this or not. If it is equal, I have to go to L1. L1 means I have to go through that path. Because with this L1, I have to do the sign extension, shift left by 2, and then add that to the program counter. Correct? And this will be the next instruction to be executed. So I have basically need to go to that particular address. But what happens if they are not equal? Do I have to go to that particular address? What will be the next instruction to be executed? Just the following one. With the following one means it's just like program counter plus 4. Yes, that's why, as we will see later on, that we will add a logic here before we actually update this guy. As you can see, again, we are building step by step the blocks to satisfy what we knew in advance as a required, basically, material or as a required task. We will see also how we can write a simple Verilog program like that if I have a branch offset. And then, of course, this basically will need to be added plus 4 and so on and so forth, and then do the sign extension and do whatever like we have already explained, how we can write a Verilog code. Everything here looks the same as I have described earlier, just adding more inputs. The most important step here is basically this guy, is how I can do a sign extension. Sign extension means what? If I have a 16 bits and I would like to write this in 32 bits, how I can do the sign extension? As we mentioned earlier, with this 16 bits, this guy, I will take that value, correct? Whatever is there. And what I will do is repeat it here, all the 16 slots that is available. If it is 0, it will be repeated that 0 16 times. If it is 1, that one will be repeated 16 times. And then concatenate whatever I had here with whatever I had from the 16 bits. That's why exactly what I'm doing here. So my program counter will be the program counter plus basically that guy, which is the branch offset, but in 32 bits format. In this 32 bits format, meaning I have taken the branch offset and then extended to a 32 bits. Yes, so I have concatenated all of the results in order to do something like that. So just like to compose the elements, we first cut the data path that does an instruction in one clock cycle. And each data path elements, of course, can only do one function at a time. And we need separate instruction and data memory as we described earlier. So we will have an instruction memory and data memory. We'll see also what will be the advance or the benefit of having something like that. So again, just like to review again the R type and load and store, if I have a load, if I have an R type, I have to have like my RS and I have to have my RT, then I will have the results, then I have to write my data to my destination register, correct? This will be the path. And as you can see from here, I have a multiplexer that it will choose either I have it from here or from any other place. Of course, with the R type, it has to instruct or it has push that I have to get it from there. This is with the R type. How about the load? How will be the path? Load meaning, first of all, I need to point out to a certain address here, correct? In order to point out to a certain address here, I have to have my source and I have to have my extension, yes, my offset. What will be the offset? And then I either add or subtract according to this my ALU operation. Now I am pointing out to the correct particular slot or the correct particular mailbox. I'm telling you, please bring the stuff of the 10th slot in that mailbox. As soon as I arrive to the 10th, what I need to do is open and take it out. When I open, so this means that the data is coming from here. It will go through that guy and go again to write the data to my memory. So I have now a path to my load word. How about the store word? Store word again, what I need to do with the store word. First, I have to allocate a certain particular address inside my memory. Second, I have to write the data from my register to that particular address. So in another sense, I'm telling you which address of the mailbox. Second, you have to take the value that is available here and put it allocated to open that mailbox and put the stuff or dump the stuff in that particular mailbox, correct? This is exactly what we will do. We have to calculate that address. How? Again, take my base address, add that to my offset. I know now exactly where I should write. Now I have to have a pipe that physically will take the data that is inside my register, copy it to my memory. That's why I have to have physically that particular connection, correct? So with all of these, as we have seen, are just like combining a lot of all of these signals, inputs and outputs, and we have shown that actually it is satisfying the load, store, word, and the R-type data path. Implementing the jump instruction. The jump instruction will have like the opcode and 26 bits address. So of course, the jump will use the word address. how I can update the program counter in this particular case, I will update the program counter actually with concatenation. I will take the top 4 bits of the old program counter, and then I will take the 26 bits jump. Yes, but 26 plus 4 is 30, but it has to be 32. Yes, that's why I will add this 0, 0. Okay, so this is basically how the MIPS designer has already allocated these things. So as you can see from the jump instruction, that all of these blocks are dimmed. Yes, I'm not using it. The jump instruction is only using that top part. That's it. Because of the jump is doing what? I just need to jump. Meaning I need to calculate what is the next instruction to be executed. I need to calculate the address of that instruction. I need just to know what is exactly next, or where is the address of the next instruction. Correct? So I don't need to do any of these. What I need to do is calculate what will be the next one, and what will be the next one, it will be just like taken from my instruction. From this guy, from the 0, 25, I have here the 26. As we mentioned, we will add the old value of the program counter, and we'll add the 0, 0. Now we have my jump address as 0 to 31, and then I will update that through here. So as you can see from here, I have added also a new multiplexer. That multiplexer will either update from the jump, or it will either update from the branch. Correct? If you look at this multiplexer, it will either, or update from the branch or from the program counter plus 4. This guy will update either from the branch or from the program counter plus 4. So each of which has basically a certain particular path. Let's say that I would like to have the program counter plus 4. So the program counter plus 4 will be here. That multiplexer will choose the 0. So this means that that guy will appear here. That multiplexer will choose the 0. So that guy will be here. So I have the program counter plus 4. If I have the branch, so the branch will be here. That guy will choose 1. So I have this guy here. That guy will choose 0. So I have that guy here. This will be at the output. And we have already described the jump. Again, I'm adding a component after the other, component after the other, in order to satisfy my previous request. So this means that I can give you any design, and you need to think by these just like small components, how to implement that design. It doesn't have to be in that class, but it can be like in an internship, or it can be in a job, or it can be in a project, or it can be in a lab. Correct? You have to think how you should design. This is my job, is to force you, just like to make your mind work, not to be a copier. Yeah, I'm forcing you, just like to always switch on the engine. And that's why I'm going with each of these blocks step by step to show you why we have this, when we will use this, and so on and so forth. As you can see from all of these, the controller actually play a big role on that. Let's check this controller. This guy, which will choose if I branch to a new address, or I just go to the program counter plus 4, correct? How I will know, just like from the previous information, that I have to branch? First, I have to do the subtraction, correct? And subtraction is satisfied, meaning the signal that is I called 0 has to be 1. Second, I have to have a branch instruction, because I might do this subtraction of these two outputs of the source, and they are zeros, but it is not a branch instruction. So I don't have to branch, correct? So I have to have these two inputs. In order to satisfy that, I have now to go to a new address, which is basically the branch address. That's why with this guy, I have an AND gate here that is taking that this is a branch address. So I have a branch, and I taking this, the second input, as coming from the 0, and this guy will not be equal to 1 unless this guy is equal to 1 and this guy is equal to 1. Correct? If any of these will not satisfy, meaning that I have to update with the program counter plus 4. Correct? Other than that, if both are 1s, my AND gate output will be 1. And if it is 1, it will choose that particular path, which is the branch address path. correct? So you always, with whatever the problem that you are trying to think about, you have to know what exactly to, or how exactly to implement, and what are the important stuff to be implemented. One more thing I would like to highlight with this graph, which is basically the ALU control. The ALU control actually plays an important role in the choosing or in the ordering or in the instruction that will go to the ALU to tell the ALU basically what to do, correct? But how that ALU control will know exactly what to do? This ALU control will have an input that's coming from the ALU up. And as we will describe later on, that this ALU up will be extracted from my instruction. And after that, it will go to the ALU control, and the ALU control will have a certain particular output according to a certain particular codes, as we will see shortly. So this is the ALU control, as I just mentioned. ALU control will have all zeros if the function is AND, this if the function is OR, this if the function is ADD, this if the function subtract, set less than, NOR. Again, I'm not expecting that you remember this. This would be given, yes, in the exam or in the quiz, if I'm asking you something that depends on that. In the lab, I don't have to give that in the lab because I know that you have access to the slides, correct? If you have access to the slides, so actually you can go to the slides and just like extract all of the information needed from there. So look closely on that. So again, the ALU control, if it is this will be the function. Okay, so that should be okay. But how we will define the ALU control in another sense, how I will have my ALU control that will have this output, not this out, or not this out. That's why we have something called the ALU up. This will control the ALU operation. First of all, I will read my opcode. If my opcode is load word, my ALU operation will be 0, 0. Okay? And then I will do an addition. Because with the addition, I can add plus or I can add minus. So I can just make it easier that as soon as I will see a load word or I will see a store word, I will have the same exactly ALU operation. And it will ask my ALU control to have an output of addition. If I decode the opcode and I will understand that this is branch equal, I will force the ALU operation to be 0, 1. And as soon as it is 0, 1, the ALU function need to be subtraction. Because I will always see if there's a branch equal. So this means that I have to do subtraction. Okay? So that's why the ALU control will be subtraction. The issue actually will come if that opcode is R-type. Because if the opcode is R-type, meaning that the opcode is all zeros. And if the opcode is all zeros, so this means that I know now that it is an R-type, but I don't know which function. In order to know which function, I have actually to decode my function value, which is located at the last 6 bits of my instruction. Yes, I have to go and look at the last 6 bits of that instruction and then decode. Okay. If that function is like that, so this means that it is add. If that function is like that, it is subtract. If that function is like that, it is AND. If that function is like that, is OR, and so on and so forth. Again, you don't have to remember all of these values. Yes, it will be given if needed. So let's say that we need to write a Verilog code in order to implement something like that. How we can do this? We will see that shortly. So again, with this ALU, if I have these, it will have like a certain function like that. So this is my ALU. I will have like the inputs. I will have like this as an outputs, and so on and so forth. So this is basically here the Verilog code in order to implement something like that. You will have the inputs, ALU control, which is basically 4 bits as we have already shown. We have inputs A and B, which is the inputs of my ALU, and I'm expecting that they are or they should be 32 bits. I have defined them here as 32 bits. At the end, I have an ALU output, and this needs to be written in 32 bits. As I mentioned, inside my always block the ALU to the left. That's why I have to find it as register. I have to have also an output 0, which is basically 1 bit. That 1 bit will be either true or false. True, they are equal, or false, they are not equal. For instance. So the 0 is true if the ALU output is 0, and this is how I will write it that way. As soon as this is 0, as soon as ALU output is 0, the 0 will be equal to 1. This is how it needs to be written in the Verilog. All of these things, by the way, will be helpful in implementing your lab. And then I will have the always block. Begin, I have to have a case. Please, if ALU control is equal to 0, please do the addition, do the AND. If it is equal to 1, do the AND or B, A or B. If it is 2, do the addition. If it is 6, do subtraction, and so on and so forth. Which basically is not but implementing that table. If it is 0, do AND. If it is 1, do OR. If it is this, do add, and so on and so forth. This is what we have already described here. So this is basically just an implementation, simple implementation of this ALU, assuming that I would like to implement that guy. How this is basically connected to these or these or these or these. So basically, if I have this, please output this. If I have these, output this. If I have these, output this, and so on and so forth. We need to know also how we can write something like that in the Verilog. So again, the function code. So I have, this is the case. This is the function code. If it is 32, please, the ALU control is equal to 2. If it is 34, the ALU control is equal to this. If it is 36, the ALU control is equal to that, and so on and so forth. I'm just copying whatever in the table here. Correct? So as simple as that. And again, you have to define the module, you have to define the input outputs, and then you will have the always block. And of course, with the always block, you have a sensitivity list here. We already explained in the other lectures what is exactly meant by the sensitivity list. Meaning that to which input you should be sensitive. Yes? So as an example, just to give you like an example right now here in the class. If you are writing, yes, something, I will not be sensitive to that, yes, because it's something you need to do. But if you begin to speak to the neighbor, I will be very sensitive to that, and then I will stop the lecture. So which of your inputs I will be sensitive to? Meaning I will have to have an action. Correct? This exactly was the always block. If I'm defining a sensitivity list, meaning that what exactly I will have here, that as soon as it changes, I have to change my output. So to which I am sensitive to. Okay? So this is just like, again, with the main control unit. Again, the R type is equal to this, and so on and so forth. With the load, I'm expecting that all of you will be aware of that. Most important thing that, of course, I have to always read the opcode, and I always read the first source, because an all will play the same role. A little bit with the RT, it's different if I have like R type or I type or whatever load and store or branch. I will deal with this a little bit differently, as we have already explained, because as an example, to write where I should write, in this case, it is this destination register. In this case, it is RT. Yes? So I have to differentiate between this and these. With this guy and this guy, of course, I have to do the sign extension. So with this guy here, just shows you the instruction, the program counter. The very beginning of the program counter, as an example, is basically that value. So I'm pointing out to that particular value, the instruction will be at the output. Simultaneously, of course, that particular address will be added to the 4, and then I will have the 504. So the 504 is now pointing to the next instruction to be executed. Again, with this guy, at the very beginning, as an example, I have this address and this address. And for instance, this address, which is like the value of 7, and this address with whatever like the value is that, is pointing out to a certain particular slots here, correct? As soon as I will have that slot address, that slot value will appear at the output. That slot value, which is 30, which is here, this 30, will appear at the output. If it appears at the output, so this means that the value that is already here will appear at this RS, the value that is already here, it will appear at this RT, correct? I'm just pointing out. As soon as I'm pointing with that address, the value that is inside will appear at the output. And this is what we can see from here. The 488, which was in register 7, and the 999, which was in register number 3, it just appeared at the output. With this guy, it will show you like where exactly to write. What is the address that you need to use for the written value? And as an example, again, I'm overwriting the 30. And for some instance, after my ALU results, the value that is here is 665. So this means that I have already override this with the 6065. So when I'm thinking about like the design from the very beginning step, so we need, of course, to have a register. We need to have an ALU. So I have like these two units to implement the R type, because with the R type, I just need a register and I just need an ALU, because I can add, subtract, blah, 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 but I'm just dealing with the register. Yes, I'm taking like 2 slots of the register, add them and put the results in the third one, and so on and so forth. So I just need these things alone. The other units that will be added, the sign extension and the memory, will be added if I have a load word or a store word. Because a load word or store word, I have to do the sign extension for my 16 bits as we have already explained. And I need to have my memory, either to write or to read. So write to or read from. Also, I have like these blocks to be added if I have a branch. Because if I have a branch, I need to use the sign extension. But I also need to shift left by 2 because I need to multiply by 4 with the branch address. Because that label, which was 2 in one of the lectures, we have multiplied by 4. Why? Because we mentioned that this word address, but I need to move by these slots inside my memory. And this value need to be added to the program counter plus 4. That's why I'm building another block and so on and so forth. Of course, with the program counter plus 4, I'm just like adding the whole. So now we have building my blocks in order to specify the branch, the load, and the store, and the R type. With the ALU control, again, as we mentioned, we will have the table. I have my ALU control lines. This will be the ALU control line, and this will be here the output. How we can do that? I have my instruction. I will decode the first 6 bits. From that opcode, I will understand what exactly to do. If I have, as we mentioned, a load word or a store word, I have to do addition. If I have a branch, I have to do subtraction. If I have an R type, I have to look at this guy. So the load word, the ALU operation, if it is load word, I will have here 0, 0. As soon that guy will see a 0, 0, so this means that I need to do an addition. If it is the store word, it's exactly the same. But if it is a branch, so I am decoding this, oh, it is a branch. So the 2 output here will be 0, 1. As soon as I will see the 0, 1, I will do subtract. So that's why I have to supply the ALU with this particular code, which is basically 0, 1, 1, 0 in this case. If I have an R type, so assuming that I have decode this an R type, then I have to check this guy. correct? So now I know that this is as an example AND. So this means that it will have the ALU control all zeros and it will do the addition. So here it shows you a little bit more complicated design, which shows like most of the stuff. It just like again show you step by step how you will see something like that, or how you will design actually your control unit from just the very beginning. So at the very beginning, you have an instruction. I'm just trying to have them on one page. Yeah. So you have now that instruction appear here. Yeah, that instruction basically appears here. So you have the opcode, this RS, RT, and so on and so forth, which is basically by your eye, you can see that this is an addition. So that values will appear here, that value appear here. As soon as I will have that, this will be at the output here. Again, as soon as I will have this, I know of course that this is now an R-type addition. This guy will be here, and this opcode will be here. It will be used to control all of these values. Branch, of course, will set to be 0 because there is no branch occur. Memory read is set, to be 0 because data memory is not bringing the read and so on and so forth. You need to know if it is an R-type, what will be all of these values according to this drawing. Correct? Then it's just like added a couple of more. That memory to register, of course, it need to be 0. The ALU up operation need to be 10 to indicate that this is an up type. So the up type, the R type here will be the 10, and then I will check what will be the function. So this guy need to be 0 and this guy need to be 1. Why? Because I have actually to choose that path. So I have to choose that path, correct? That's why this need to be 0, correct? Because this is an R type. I have to choose that path that will appear here. For the register write, I have to have it 1 because now I am doing the addition and I have to write to the register. So now with this guy, I have decode the function. With this function, I know now that is an add. If it is add, I will actually, with the 0, 1 that is coming from the opcode, I will know that this is an addition. I will force the ALU to do the addition. If it is doing the addition, as you have seen here, I just take these two values. As you can see, it add this and this have the 88. That guy will pass through here, and just will be written in my register. Of course, in order to have this path, I need to have this value 0, correct? That's why if you look at this memory to register, it is 0. So of course, this is something that you just need to think about it. I'm not expecting that you will remember it, but this is just like a design, yes? So please don't ask like, do I have to remember this? I mean, of course, I'm not expecting at all that this is like needs the memory, because this is just from my perspective. You need to understand what each block is doing and why I choose this value. Of course, finally, the results will be written, which is 88 to a certain particular address, which is pointed out by that guy. If you look closely here also, if you look closely at this guy, you will see that I have also another multiplexer here. Because that multiplexer, in some cases, it will take basically the RT as my input, my destination. In some other cases, it will take the RD as my destination, correct? Because this is with the load word and store word. That's why it is a little bit different. That's the need basically behind that multiplexer. And in this case, I have to go through this. And in order to go through this, I have to have this guy equal to 1. 1 Why? Because I have to choose that particular path, correct?